solution. I think I did. But generally used. All right. Well, thank you everyone for coming. Today we have a meetup that we're fortunate enough to have Bernie Kerr, who's a Kiwi who's now living abroad and works with the International Space Station. So we'll hand it over to Bernie now and let him give the introductions. If you do have any questions, you're welcome to tweet us throughout this, just using mentioning @Kiwi Space in the Twitter feed, and we'll try to answer them at the end. Well, thank you everyone for coming. Today we have a meetup. So we're fortunate enough to have Bernie Kerr, who's a Kiwi who's now living abroad, and works with the International Space Station. So hold on. Now figured out what's going on. Bernie, can you hear us now?
Version and also about a 10-second delay. So.
Yeah, Bernie, can you hear us now?
Yes, I can hear you. Can you hear me?
Sorry about that. Had a double broadcast going on, to ignore that.
No problem.
All right, you're live. Go for it.
Okay, so I'll just move into my presentation. First of all, welcome everybody. My name's Bernie. As Mark said, I'm a Kiwi. I was born and bred in Southland. I moved. Well, I did my overseas experience just before I was 28. I moved to England, and have since moved to Germany, where I've been working for the International Space Station. So if you can now see the presentation, we'll move to slide 2. And first of all, this is basically the presentation overview. I want to just talk about the company that I work for, the job that I do, and maybe perhaps talk about you guys' possibilities of working in Europe, or getting a job in Europe if you so wish. So the company I work for is called Insign AG. It's which is AG is a German word for a company, and we specialize in Insign means innovative systems engineering. So basically, we're a systems engineering company. We primarily are concerned with human space flight operations. We also do mission-critical software. We develop simulators and emulators for various people around the world. We're heavily involved with satellite operations. Europe and worldwide, we do security networks, and we also have a 3D visualization section in our portfolio. So I've got a couple of nice pictures here. I'll just move to the slide 4. So what we do is we combine we make simulators and emulators for things like drones, or for helicopter-mounted equipment that are used for crowd control, by the police, by the military, or for power lines, pipeline construction, and whatever. So that's one of our side interests. And you can see here, this is a camera. It's a airborne mounted camera. It's made by Westcam. It's about a 30 kilogram all-weather infrared military spec camera that's used for, like I said, all sorts of applications around the world. So and we make, while Westcam sell these cameras, these turrets, it was too expensive to actually train and have a helicopter pilot and an operator flying in real time. So what our company has done is developed an emulator, and I showed you the picture of that before, so that we can train the pilots and the operators to do this. So going back to what I do, I moved over to Germany quite a few, well, in 2000, oh no, it's 1990, and so what does a satellite controller do? Well, basically I got the manuals out and I read the effing manuals, because there's no such thing as doing a degree or whatever to train how to become a satellite controller. So basically I got out the manuals of how this one particular project that I was working on called ROSAT, how it was flowing, and I read the manual. And after getting this job in Germany, I came here. I launched the satellite. I was on the launch team. The satellite ROSAT was supposed to fly for 2 years. It actually was very well built, and it flew for 7 years. And it was a satellite that was basically instrumental in finding black holes and supporting Hubble in a lot of research for finding black holes. It was launched at the same time as Hubble, but it actually did a lot better and a lot more research on black holes and what have you. So as a bit of a background, I've worked on on various missions. You can see a bit of the few missions that I've worked on. I've worked on MOMS. It was a camera that was mounted on the Russian spacecraft Mir. I launched various Eutelsats from the German Space Operations Center here in Munich. We had a couple of other spacecraft. Equator S was a very interesting project that had it was a satellite that was measuring the electromagnetic fields around the Earth. It had an apogee of 500 kilometers and a perigee of 500 kilometers and an apogee of about 80,000 kilometers. And one of my more interesting things was hitting the button to launch the rocket that was 400 Newton meters that sent this into the correct orbit. So that was one of my more interesting jobs. We had an Abrixis satellite and another CHAMP satellite. You'll see that this is the satellite that I was talking about, ROSAT. When it was launched, the solar panels were folded away and also the antenna. So these were pyro-bolted. We launched the satellite, solar arrays, etc. after we had done the commissioning. It's actually quite an interesting satellite because the telescope is one of the most finely ground mirrored shape lenses in the world. They're about 2 meters long. They're circular, and it's made so that it can bore sight into very deep space, and with a very good gyro control systems, we were able to bore sight deeply into space and go well into millions of light years into the past. And just for your information, you probably all know about some satellites like Eutelsat, or Eutelsat rather. This is just a telecommunications satellite. We did a lot of the basically they're launched on a launch vehicle, be it Russian launch vehicle or European or American. We take over the once it's been launched and put into the correct orbit. We start commissioning it for about 3 months, and then we hand it over to the payload community or the contractors to actually start using that for telecommunications, for telephone, internet, whatever. So, and the main thing that we were doing as a satellite controller on this is to make sure that the ranging, the height at a geostationary orbit, made sure that the footprint of it, where it was looking and that it was actually covering, was exactly what who should be seeing the footprint and who shouldn't be. So it's a matter of doing a ranging and increasing the elevation or decreasing the elevation depending on the footprint we're after. So having done satellite operations for about 10 years, I moved into the manned space mission. And the manned space mission is based also for the whole of the European section on the ISS. It's a module called Columbus, and it's flown by the Columbus Control Center here at Oberpfaffenhofen, which is just outside of Munich. It's a control center where we monitor, we control and command the Columbus module on the International Space Station. So a nice picture of the space station, in case you don't know what it looks like. But to give you a rough idea of what the space station size and geometry and telemetry and whatnot, it's about the same size as a rugby field, including the tri-zones. So it's about 120 meters long. The internal volume, it's about the same internal capacity of a jumbo jet. It flies around the world. It has an orbit time of 96 minutes, so it's flying at 7 k's a second. We have basically complete, almost 90% coverage on an S-band and about 95% on a KU band. The S-band is used for voice and telemetry command, and KU band is used more for video and high data rates. So we have all around the ground stations around the world good coverage and good capabilities of commanding and controlling the Columbus module. I just wanted to give you a rough the dimensions of it. It's a very, very small module in comparison to the size of the station, but what it is in a laboratory, and it's used for doing payloads. And there's various payloads. It's human biology, fluid science, microbiology, and loads of other different scientific applications. I just wanted to show you that there's been 2 new payloads added here. One is called Rapid Scan. It's a downward-looking camera that monitors the wave sizes, and it looks for possibilities of tsunamis, and also informs shipping traffic of any possible larger waves and things to look out for. It also has a solar application externally, which measures the solar flares or solar intensity over any given time, and things like that. So my job as a NASA and ESA, well, NASA is the National Language and Space Administration. It's the US side of things on the space station. Just to give you a brief overview, we have various international partners: Russia, America, Canada, Japan, Europe, all working together in cooperation to make this space station productive, do science. And my job is a Stratos, that's my title. I sit on console and 24/7 operations. Around the clock, we have one person like me that is looking after everything within the Columbus module: thermal, environment, power communications, and data handling systems. The distribution you can see on this slide. We communicate with NASA and JSC, which is in Houston, and also POIC, the Payload Operations Integrations Community, which is in Huntsville in Tennessee. And you can see the distribution of all the international, all the European payload communities, all communicating with the Columbus Control Center. So I've got a picture of my work environment here. You can see this is one of 3 control centers, control rooms that we work on. We have, at any given time, about 5 people on a 24/7 basis. We have a flight director that sits in the main center here, the Stratos position, which is commanding and controlling all functionalities within Columbus. We have ground controllers and ground control people that are monitoring the air-to-ground links or the ground-to-ground links to make sure that data is relayed and transferred or stored. Video is put on the big screens when we need it. We have about 6 external cameras around the space station. We have cameras mounted on the robotic arms, which grapple either visiting vehicles like SpaceX or monitor the docking of the shuttle, or can do surveys of any damage, for example, like the shuttle exterior tiles or whatnot. Or they also monitor when the astronauts are doing spacewalks or whatever. We also have various internal cameras that we can turn on or off at any given time. This is an example of what's happening at the moment. We have, at the moment, only 3 astronauts on board. Normally we have 6 astronauts. We have 1 European woman astronaut, Samantha Cristoforetti. She's a very, very intelligent and well-schooled astronaut. She's got a military Air Force background. She's got a master's in space science, and she's very well equipped to do this role up there. She's been up there for 4 months. She's doing an extremely good job. We're starting a very interesting campaign now where there's a couple of astronauts. Scott Kelly, he's going up there and he's going to be spending with a Russian counterpart a complete year, 12 months on the station, which has never been done before, to check the effects of long-term space duration with the hope of leading us to better information about how we are going to get off this planet or do long-term missions, for example, to Mars. He is actually an identical twin. His brother, Mark Kelly, has been onto the station, and they're using both of these astronauts as a guinea pig to check the differences in their muscle density, bone density. Osteoporosis is a big problem in space. So basically, they're going to do a control of Mark and Scott to check the differences in their body functions or compositions of bone mass, and what the long-term effects of space travel is. There's another photo of this is the module of Columbus. It's stuck on the very end. On the other side, we have the Japanese module. This is the trunk of the space station. We have the American section here, and you can also see down here. This is SpaceX. It's the newest, and it's the commercial side of the American space business, where America is trying to be less reliant on the Russian Soyuz system to, now that the shuttle has been retired, to get astronauts to and from the station. And you'll see here also the space arm, which is used to grab or manipulate astronauts around during a spacewalk, or also to grapple vehicles such as the Japanese HTV. Basically, the vehicle flies very close to the station, and the robotic arm is moved to grapple the visiting vehicle and then dock it onto the port. This is SSRNS. It's made by the Canadian Space Agency. It's a very clever piece of machinery. It's actually got 7 degrees of freedom, but not only that, it can walk itself down and up the station. It's mounted on a trolley, on a guy that can go up and down the station, but also it can basically grab grab a part of the station and let go from the other end. So it's sort of like a massive, great arm that can grab, hold, and move around the station. It's a very, very good piece of machinery. So we can move on now. Inside Columbus is. Has anyone got any questions, or Mark, am I moving too fast or too slow, or is anybody bored, or you okay? Okay. Everyone okay? Thumbs up. All right.
Sorry, we had you on mute, so sorry. Sorry.
Oh, okay.
We were muted.
Okay.
Anyone got any questions at this stage of the meeting?
Okay.
Back to you, Ben.
Okay. Just interrupt if you don't understand anything, or we can talk at later at the end of the day. End of the day. So this is looking from the hatch. I've got bad echo here. No?
I'll turn my mic off. Hold on.
Okay. That's right. So this is looking from the hatch of Columbus. It's going. It's from the node 2, and it's looking straight into Columbus. It looks a bit of a mess at the moment, but basically we've got a deck which is loaded with most of the systems. It's got the water pumps, the computers, the power distribution units. Basically along the bottom, down the back, we've got cameras, we've got the data management systems, and here along the left, the forward and aft side of the Columbus module, we've got all the payload racks, which are which look a bit untidy. These things here are stowage compartments, because space is at a premium on the station. We have to store things. We have to be able to locate them, use them, and then restow them so that they don't float around everywhere. Otherwise, it's just going to be chaos. They're going to end up in fans and just get in the road. So this is the internal. This is what Columbus internally looks like at the moment. And some of the payload racks, for example, we can see here. This is basically what they look like. This is BioLab. It's for biological science. We've got a glove box where they can put on gloves and do biologically dangerous experiments. We have fluid science. They check the motion of fluids in space, or also they have combustion chambers. They check, they measure, calculate, and monitor how combustion works in space in a weightless environment. And we have also compartments. We've had a few experiments. We've had spiders in space. We've had fish. And checking how they relate or how they function in a weightless environment. So, as I said before, Columbus is a laboratory. It's made for science. It's made to do experiments. And my job is to ensure that the power is turned onto these payloads, that they can these astronauts can get their experiments done. They have procedures that they have to run through. We have a schedule that is basically down to every last 5 minutes. The astronauts have a very strict regime where they do 8 hours work, 8 hours play, 8 hours sleep. Joseph Savage, we can thank for that. But the astronauts, over time, they do get tired, so they stick to this regime where they work 8 hours. And included in that is a 2-hour physical exercise. They either get on a treadmill, they have to do elastic, or they have to do weights, or they have to climb on a treadmill. And this is very, very important because they are the muscle. The muscles do tend to get very, very lazy because they're floating around in an environment. So they have a very, very strong physical exercise regime. I'll just put this in here. It's a photo of, for example, of what our telemetry looks like. you can see this is the water flow systems. We have an area of air conditioning where we take the air down to less than 4 degrees so we can remove the condensation from the air. It moves over and cools the payloads. Cooling and heating is a very big issue, so we have to maintain the air temperature at around 20 degrees, so the air conditioning is very important. And any excess heat is sent back to via heat exchangers to the American system, and the American system uses ammonia to externally outside the station via heat exchangers. So ammonia moves outside the station. It's cooled by the thermal radiation and dissipates into space. This is, in fact, what's the word I'm looking for? In comparison to the Russian system, the Russians don't use ammonia; they just use water. So the Russians have a long experience in manned space missions with the Mir project, and they did not go down this route of using ammonia, which can be taken down to freezing, well, as a freezing point of at least -40. They prefer to use water because ammonia is toxic. And I don't know if many of you have been following the space station, but ammonia is toxic to humans. It can be smelt basically once, and if it's smelt, it gets into the nasal cavities and becomes it goes into the lungs and is basically very, very toxic. So what we do is we have loads of emergency procedures where we have, well, there's about 4 major emergencies where we have on station. We have a fire, a rapid depressurization, a meteorite strike, and the other one is ammonia leakage. And we had ammonia leakage the other day. It was a false alarm, but basically what happens is everything stops, operation stops. The crew go to their safe haven. They put on their masks, and if it's a real one, they go down to the Russian segment. All the cameras go off. They strip off all their clothes. They go into their Soyuz. They put on their spacesuits, and they're jettisoned basically straight home. So ammonia, while it's very, very toxic, it's a very, very possibility that if it does go wrong, that they have to leave the station. Another one is fire, where we do loads of training and loads of simulations, testing how we react to fire. Every month we do a fire drill. So they simulate a fire. They have their procedures where they have to go and don their masks. All the fans that are around the station, the moving air around the station, go off. And they have their drills where they say, okay, is it a real fire? They get instruments where they test the levels of combustion levels, so that they test the toxicity of the air, and if it's too toxic, they get into their Soyuz and they pull the pin and they come home. So that's part of my job. We practice and make sure that we keep the astronauts basically alive. I just put this in here because things fail on the space station. I don't know if you can see the quality or the intensity or the quality of this photo, but what these are, what is shown here is water flow on-off valves. So these modulate and control the temperature by mixing hot water and cold water to keep the temperatures at the same place. What's actually happened here is you've seen build-ups of condensation on the outside of the valves, and it began a rusting process within the valve, and the valve has stopped moving, so it's stopped modulating, and we have had to do a change out of these valves, which is a long and arduous process because the astronauts have to get behind the payload racks. They have to tilt racks down, they have to get in there, they have to completely dismantle and reassemble the new parts. So a very, very involved process. It's not a process which we like doing, but things do go wrong on the station. And as Mir has taught us, the Russians were basically were keeping Mir flying, even though it was basically rusting and the lines were corroding and was basically falling to bits. So, and this is not slowly happening to a much slower rate. I put this photo in here. It's one of the photos that the astronauts take. They take loads of photos, but this is one of Munich, snowbound Munich. If you've been here, it's a Russian. Sorry, this is a Andrew Kerr. He's an astronaut. He's looking at the cupola. The cupola is one of the favorite areas where the astronauts hang around in their spare time because it's got 5 major windows where they can look out, and 1 major window is facing straight down. So they spend a lot of their free time here photographing the Earth and observing bits and pieces. They have big shutters that come down and close over these windows. These windows are about 15 centimeters thick. They're very, very thick glass because they have to withstand quite a bit of temperature variation and whatnot. But it's a favourite place for the astronauts to hang around. So just to give you an example of the size of the space station, one of the things the astronauts really like doing is going for spacewalks, and I don't know if you can see you can see the solar panels here. They're quite huge, and this here is the thermal radiation panels, which is never looking to the sun. It's always away from the sun. It dissipates the heat. But you can just see here one of the astronauts on a spacewalk. He's doing a repair. He's actually laying cables for the new SpaceX, which is going to be docking to another docking port. But
we're struggling to see the astronauts. Can you describe that?
Okay. Can you see where I've got my mouse here? The mouse. He's basically this is the center. He's just there. You can just see his legs, and he's lying along the vertical plane of the spacecraft. You can hardly see him, but just to give you an idea of the size of the station. And there you can see he's actually he's just got off the space arm, the SSRMS. Basically, they stay on the end of the. Sometimes they stay on the end of the arm, and they are moved around by the robotic arm to the position that they want to, and they do their work there. The astronauts have always got to be fixed to the station with at least 2 fixed grapple fixtures. So they've got grapples. They've got guy wires that are always running up and down the station. About 5 years ago, there was a woman, space astronaut, I forget her name now, but she had a toolkit which was stretched to her, and it was full of grease because they were smearing grease onto a bearing, and she inadvertently undid her clip so that she could empty out this grease, and unfortunately the toolkit floated about a meter away from her, and she couldn't cut it back with the extension of her cable. So NASA and us watched this toolbox float away, and this became a piece of space junk and has to be tracked for the rest of its life. It was a disastrous action for many people, and it virtually caused an end to her spacecraft career, because it could be that the space station on another orbit, depending on the trajectory of this toolbox, could run into it or become space junk. And space junk is a very, very big problem these days because there's so much, so many bits and pieces up there. Everything that's basically bigger than 2.5 centimeters has to be tracked by a dedicated computer, by NORAD, which is the American military tracking system. Because if the space station is flying 7 k's a second and a particle, no matter how big, even if it's a small bolt, is also traveling in the other direction, it's going to, and if it hits any of the space station, it's going to rip through it. It's going to cause major damage, and the astronauts are basically, they're coming home if it hits. Depending on where it hits, if it hits the solar arrays, it's not so bad. But if it hits the main body of the space station, then that's very, very critical. This is a complement of the crew here. This is the Samantha Cristoforini. I won't go through the others. There's generally 3 Russians. The commander of the space station is like a boat or like an airplane. The commander has the last say. They say go, stay, or get off, and they command the station. They have the last word. It generally rotates between a Russian or an American and sometimes a European or a Japanese, Canadian, whatever. But it's a very big, responsible job, and yeah, but it's also a prestigious job. So I'm nearing the end of my presentation. So this is just another photograph inside Columbus. I mean, the astronauts have a lot of fun on board in their free time. They just goof around, and there's nothing better than seeing them flying down the length of the station and then coming to a corner, grabbing a handrail and spinning around a corner at 90 degrees and just going down another direction. But they do loads of experiments. They do loads of publicity events with radio stations, television, and they do things like drinking water globules form circles, and they swallow a round circle of water, and they do loads of experiments. And some are very good, and there was an astronaut, Chris Hatfield. He was a very, very good Canadian astronaut. He also made a copy of Ground Control to Major Tom, David Bowie's song, and that went viral. So they do have a lot of fun up there. They have to work. They're top of their game. They've got once they get to the station, they really have to earn their keep. But they do enjoy themselves up there. So last but not least, I was going to give you guys just a couple of links. I mean, if you guys, and I take it you're all studying engineering, or you're hoping to get into the space engineering business, I'll give you a few links. This is the company that I work for in Cyan. There's another, LinkedIn is also a very good format for finding jobs in Europe. I just gave you this other link here. This is Heavens Above. It's a guy in our company makes this website. You can put in your coordinates and see any satellite or any piece of space junk that's flying around that's visible generally during dusk or dawn, but from your coordinates. So you go to the website, put in your coordinates, and he'll give you all those visible satellites at any time from your coordinates. It's quite an interesting website if you want to see what the satellite is flying over you at any given time. So, and the last slide is that what are we doing all this for? Well, basically, we hope to get off this planet at some time, be it the Moon or be it Mars. The experimentation we're doing, I hope will be it plants or animals or combustion or new methods of solar arrays or propulsion or whatever. Everyone tends to say, all this money we're spending on research, what does it actually do? But it does have some major spin-offs for ground, but it also is going to help us to get to Mars or beyond. So I open it up to anybody. If you've got any questions, I'm pleased to take any questions.
Cool. Well, thank you very much. It's good stuff, Bernie. And you want to start us off with the first question?
Sure.
Just speak nice and loudly and slowly. Is there anything else?
Kiwi.
Hi.
Introduce yourself.
I'm Peter. I'm a software engineer. Well, usually a space entrepreneur. So if I'd like to put an experiment on the ISS, who do I call? Do I call you?
if you want to work on the ISS, or if you want to get a job working with a software developer, or
maybe like I have a science experiment and I want to put it on.
Okay, right. That's a very good question. We have all these payload centers all around Europe, and they're looking for ideas for what we can do on particularly in Columbus. So if you've got an idea, then you can go to ESA, which is the European Space Agency, and make a proposal to say, I want to study fluid science, or I want to study the effects of gravity on a snail, or on a fish, or on plant life, or whatever. And so you make your proposal, they'll say, this is a great idea, or this is a load of rubbish. They'll assess it, and then they'll say, okay, has it got application on the space station? Can we use it? Is it going to be beneficial? And what's it going to cost? I mean, basically, it's got to be a cost-benefit analysis. But if you've come up with a good idea, then they'll certainly look into it. They're looking for applications. They're taking applications all year round. So if you visit the ESA website, ESA EuropeanSpaceAgency.com, they'll entertain your proposal. And while I'm on that, one German guy had a proposal very recently to see if plant life could survive externally on in a weightless environment outside the station. So they've mounted this lichen, which is like a form of moss or fungi. They've taken it off Mont Blanc. They've take a sample and they put it outside the space station, so it's in a weightless environment. It's extreme hot and cold, no oxygen, and they've left it out there for 6 months, and they're going to see if it actually survives this, and then they're bringing it home to see if it's survived. And it'll give, basically it'll reinforce the idea that plant life can survive in a given form on an asteroid or on a meteorite or whatever, and that's how plant life or biological forms of life actually came to our planet via meteorites or whatever. So if you've got a great idea, either get it to me, or I can forward it to ESA, or you can go straight to ESA. But we're always looking for ideas about how we can show that we're doing good science up there.
Thanks. Cool. Yeah, next question. Okay, well, I'll shoot. What made you take the switch from satellite operations over to the Columbus module and manned space mission?
Well, yeah, satellites don't talk to you. Satellites are pretty boring, really. They just turn on and you come acquisition of signal. You do your stuff. You uplink your orbital elements. You uplink your data, and then it goes. If it's a low Earth orbit satellite, and then it goes away after 10 minutes, and 90 minutes later you take the data off it and send up the whatever you like. It's pretty boring. With astronauts, it's really dynamic, because they're talking to you all the time. They call down and say, "Hey, Bernie, where the hell did I put that socket wrench?" Or, how do I get this damn screw out of this? Or, it's astronauts are great. They can't do anything wrong, so if you make a mistake, you have to suck it up and take the blame for them. But satellites is a bit boring in comparison to manned space missions. So basically, I had enough of satellites and went on to manned space mission. But saying that, once this project is over, I'll probably be going to the Galileo project, which is the GPS, European GPS system, which is just across the road from us. And the GPS Galileo system has got 24 satellites all in low Earth orbit, and it'll be used to basically revolutionise the whole of the European air traffic control system or fleet management or whatever. And it'll take over from the GPS system. But yeah, satellites after a while get a bit boring.
Cool, thank you for that, Bernie. Any more questions?
Hi, my name is Saki Bernie, and I'm actually in business with space flight and things like that. So my question is, what do you think about the Mars One mission and how complicated to kick off the new project?
Did you hear that?
No, I didn't. Could you repeat the question? But
so the question was, what do you think of the Mars One mission, and like how complex would it be to pull it off, etc.?
I always quote Edmund Hillary on his quote when he got back from climbing Everest, and the British had a lot of goes at getting up to the top of Everest, and that a lot of them failed. And he said one of the major aspects of mountaineering or research or what we're doing is to get back alive. Mars One is working on the premise that we're going to send people to Mars and they're not going to be coming back. It becomes a moral issue if we can morally accept that we send people basically to their deaths, or not to their deaths, but they're never going to be coming back. Okay, they're talking about sending a mission to Mars, and then they're talking about sending another mission, and by the time the second mission gets there, the first mission should be made enough fuel or generated enough propulsion system to get them back. I can't see that happening, basically. So it's a moral issue of sending people basically on a one-way ticket to Mars. The other question is what they're going to do when they get there, and if they're going to find water, and if they can survive there. It's a tricky one. I know that they had thousands of applicants. They had some very good applicants, and I think they've thinned it down to about 1,000 people. So I don't know. Mars is a very long way away, and it's a very hostile environment. I wish the people that are going there a lot of luck, but I know I couldn't do it. I know that some of the astronauts that are even in space for 6 months, they come back old men and women. So sending a person for 18 months to Mars, I mean, it's tricky. It's a hard environment out there. So, it's virtually a death sentence, if you ask me.
Cool, thank you. Any more questions?
Hi, Bernie.
Yes, please, nice and project loud and clear.
Hi, Bernie. Alan here.
Hi, Alan.
I was just wondering, what the ISS is aging, how much longer do you think it'll last, and what might happen?
So
okay, I'll have to get someone to repeat that because the audio is a bit bad. So what was the question again?
Well, the ISS is aging. How much longer do you think it will last?
Oh, okay. Oh, that's a good question. The space station, it started being built in about 2000 with the Russian segment, and then they've put on bit for bit for bit. So I mean, the aging of the space station is varying. I mean, Columbus, the module, was built with a life expectancy of 5 years. So things are starting to go wrong, and when parts break down, we've got spare parts up there, but if something that breaks down and we don't expect it, then we have to fly it up there. and obviously every kilo costs a hell of a lot of money to get up there. So good German and European engineering has made sure that the redundancy or the functionality of a lot of these valves or heaters or heat exchangers is very, very good. So Columbus is actually in a very good situation. However, there are parts that are aging very, very quickly because of the harsh environment. So there's going to be a stage where they just, the Russians are going to say, we're not going to invest any more money, the budget will run out by the Americans, or people will just say, it's reached its sell-by date, they'll shut the hatch on probably one of the modules, and they'll stop the cooling, they'll stop the ventilation systems, and they may just shut it off section for section. The Russians have actually been very clever in this, in that they've made everything that they've done on this non-reliant on the American system. So you've got a larger Russian system and a large American system. Basically, at that interface, the Americans could say, we're shutting up shop, we're going home. The Russians will say, oh, I think we're going to keep it going for another couple of years. So you could have eventually two separate modules flying around. And I wouldn't be surprised if you've got the Chinese that would buy a slightly used space station and use it for their own experimentation, or you get someone like maybe Virgin Space that will set up tourism. There's talking about putting modules that are inflatable, and they can form very, very large areas for space tourism. So I wouldn't be surprised if someone like that comes along and takes the risk and sets up a space hotel. So you can't say basically that the stations is going to be, it's going to run out of money, because by 2020 everyone said there's no more money. So I think that's when the budget's going to stop, and it's going to be up to entrepreneurs to say, okay, I'll take a used space station, I'll try and make some money out of it. And I think that's probably, if you guys, you entrepreneurs around, think about it. A used space station, I don't know what it's worth, but it could be a viable or an interesting proposition by 2020.
Cool, thank you. Next question? Next question? Oh, yeah.
Hi, Marcus.
Come closer, man.
Can you hear me?
I can, yes.
So I'm Marcus from Germany, and one question I've been asked myself for a while now is, they've been doing research in human physiology in space for a long time now, basically since the beginning of the human space travel. Do they think they actually have now a good handle on the problems for long duration flights, like or is it still open? They don't really know how to deal with it.
So I'm sorry, I'll have to get you to repeat the question, or Mark, could you just give me a précis of what the question is?
So the question is, they have been researching the human body in space for a long time.
Ah, yes.
And do you think they have, or do they have now actually a good idea how to deal with long duration space flights, and how to solve these problems that occur, like muscle loss and bone loss and all this stuff?
If I understand you correctly, you're asking about the impacts on the human body about space flight. So basically, fluids move around in the body quite a lot. So when you've got gravity, most of the fluids are dispersed around the body. But in space, they gather around the head, around different regions of the body. One of the things that all astronauts find is they get back pains, and it's because of the extension of their spinal cord or their vertebrae within their back, and it's the extension of them that causes the pain, whereas on Earth you get compression. And one of the experiments that are happening soon is that wearing this thing called a spacesuit, which actually holds the, compresses the body. It's like a massive, great wetsuit, and they strap it on, and it compresses the body so that they don't get this elongation of the spinal cord. That's a very interesting experiment. A lot of them also get problems with their eyes because their eyes start bulging, and they have to do regular eye scans or ultrasound scans of their eyeballs to check that their eyeballs do not extend too much, and they start having difficulties with their vision. Another thing is the porosity. They come back osteoporosis. The radiation is very high, so they come back with very high osteoporosis, which is another thing they try to combat. When there's high radiation levels, they have to go to safe havens, and they sit in this thing which is a lead-lined cabin when they've got high radiation levels. So yeah.
It's in my phone.
No, it's in the laptop, so come close. Up over there. It's here.
It's in my
It's here. So, yeah.
So the question is more, if you would go now, if you would have the technology to go to Mars, which is now would be a long flight, 12, 18 months or something like this, would this be basically approved by the doctors or not? So have they a good handle on those long spaceflight issues or not? That's the question.
The question is how do you keep a guy amused or a woman amused for 18 months? They can't go for walks.
Also medically.
Medically and physically and psychologically, it's a real problem. They're locked up. I mean, if you've seen some of these sci-fis, they basically put them into a state of cold storage. You know, they go to sleep. That would be the best solution if we could possibly put them into sort of a semi comatose state. That would be the easiest solution. But then again, you know, you've got the muscle dystrophy. There's loads and loads of problems we haven't even begun to address, let alone the fact that how do you feed them? You've got to send all their food with them. Plant growth is very, very difficult in space. You know, the roots don't know the up and down. So there's loads of problems that we've got to address before we even start sending people to Mars. And like I said, it's a one-way trip basically. So morally, and how do you address that issue? And the other thing is that even if they do get there, are they going to be mentally stable and psychologically stable? There's a lot of issues there. It's tricky, but yeah, you know, that's why we're doing all these experiments. That's what we're working on. So, but are you going to volunteer? Do you want to go? Would you like to go to Mars? Sure. Hands up. Who wants to go to Mars?
Just one. Just one.
Really? No one else? Who would like to go to the space station? Anybody? Yeah, I'll hold my hand up too. I would only go for a short duration mission. I'd go for 12 days. There's one starting on the 1st of September. I don't know if you know about it. Sarah Brightman. She was married to Andrew Lloyd Webber. She's going to space to sing an aria. She's going to. She's been sponsored. It's cost about 25 million for 14 days in space. It's not cheap. But she's got most of it sponsored by the recording studios where she's going to sing in space, even though you know space environment sound doesn't travel. But well, she's going to do an opera. So it's going to be interesting. But it's amazing. The Russians have tourists, and they're quite keen on collecting the money for this because it pays for a lot of things for the Russians. So 25 million goes a long way in Russia, but they also put them through very, very strenuous tests. I don't know if you've seen these G machines. They put Sarah Brightman in them, and they thought, oh, we'll make her throw up. So they spun her around quite quickly, and she was pulling about 4 Gs, and she coped quite nicely. Even her heart rate didn't extend beyond the normal realm. So she did very, very well. Looking forward to her being in space. But space tourism is a moneymaker, but basically they get to the station and they're not allowed to touch anything. They don't do anything, but they hang around the cupola. They look down at the Earth all day. They take loads of photos, and okay, sure, they sing an opera, but yeah, it's looky, no touchy. Pretty boring 14 days looking out a window.
Cool, any more questions? I'll come a little bit closer, but
yeah, sure. Hey, Bernie, I'm Isaac, Kiwi. I'm a software engineer as well.
Hi.
I also have a question around software. So, do you see a lot of growth opportunities or demand for software in the space industry in Europe? And if so, do you need space-specific knowledge to get into that, or can you enter and learn that along the way?
There's loads of software applications that we use. We use various different levels of software. In our particular company, we're investing heavily in 3D software. 3D is big business. So there's hundreds of different applications for software specialists. I can't recommend any particular language or any particular direction to go, but yeah, if we need a particular application, they just throw money at the software developers and say, we want this, and it's got to be this, and it's made. And the Americans have got so much money, they just throw money at a problem. But yeah, always software engineers needed everywhere. And I mean, our company, we not only do ground systems, we also do space to ground, networking and data transfer, data development. It's storage. It's big business, and yeah, always needed. And you don't necessarily have to have a space background. I mean, it's a help if you've got a aeronautical degree. And if you want to go to space, you're obviously going to have a very, very good degree or a doctorate and a military or Air Force background. So for all those guys who want to go to space, get studying.
Following on from that, then, Danny, how hard is it for a Kiwi to get a job working in European space industry?
If I was a student, like I presume you guys are sort of getting towards the end of your degrees and your study. ESA has programs where they take on young students. It's called the Erasmus project. I would apply to a European Space Agency for an Erasmus project. A lot of Indonesians or a lot of Asians are accepted, and I work with a couple of them that have done a 6-month internship to the European Space Agency. We also do, we take on interns for very short periods, our company. The trouble is, it's often an issue of getting a work visa as a non-European. As a European country, they have preference for a European citizen, obviously. So you generally have to be sponsored. It becomes difficult, but you can get study. If I was in your position, you want to get into the space industry, I would apply for some of these study grants or internships with the European Space Agency. Get 6 months under your belt, get another 6 months internship at a small company like ours, and then if you're good enough, you'll be picked up. But there's ways and means of doing it. You just got to be clever, and you've got to be a real go-getter. You've got to really get out there and go for it.
Cool, thank you. Any more questions?
So how much
much of the experiments are actually run from the ground? So how much are the astronauts involved in them?
It depends a lot on the experiment. Obviously, we're allocated as a Europeans. We've got an 8% budget of the crew time. The crew time is allocated, 8 hours a day, and we get 8% of that. So, if the astronaut has to go and do an intensive movement of a sample into a glove box or into a centrifuge or whatever, every minute he uses it is taken out of the budget. So the more we can do on ground, the better. And if the experiment just needs to be heated or cooled or lighted or whatever, we try and do most of that by ourselves on the ground. But when it comes to moving samples or things like that, we have to get the crew to do it. And that comes out of the budget. And of course, if things go wrong, if things break, then that comes out of the budget too. And if they've got to repair something, if they've got to take something apart, rebuild it. That's 6 hours. That's a lot of time. And not only that, but we have to do all these procedures. We have to prepare everything so we save time for the astronauts. So we prepare it on ground really meticulously, and it's reviewed and reviewed, and make sure that we save crew time. So, yeah. The more we can do on ground, the better.
Bernie, out of curiosity, why don't NASA, I believe, is starting to do robotics, like robotic humanoids. Does ESA have any similar projects? And I guess how important are humans in the loop if you have that capability?
Yeah, robotics is going to be big business. They've got this thing called Robonaut. It basically looks like RoboCop. He's got a torso, he's got a head, he's got cameras, he's got 3D vision, and he's got arms. The problem with robotics is the tenacity and the feel, the feedback of picking up an object or screwing a bolt in or moving a switch. It's the tenacity and the haptics of the robot, and it's the feedback. Like, you can't get a robot obviously shaking hands with someone and he's going to crush their hand or whatever. That's the problem. It's the feedback and the tenacity and the haptics of the robot. And this is what they've found also with the robotic arm. You can move an arm, but it's getting, when it gets very, very close to the interface, is it going to damage that interface, and is it going to cause some damage? Because if it does, it damages something once, then that's non-repairable, and you can throw it away. So I think this is the growth area in robotics, is the feedback issue, the tenacity, the haptics, the feedback. That's where the growth industry is in robotics. And also, robotics is all very well and good. We've seen it with the Mars voyages, we've seen it with the rovers, whatever. If things break down, they've either got to have built-in redundancy, which is you can make a redundant wheel, or you can make a redundant CPU or whatever. But the question becomes the trade-off: how much redundancy do you build into it? And if things go wrong, have we got a workaround? And if we haven't got a workaround, is that the end of mission? Is that a failure? Is it a one failure scenario? So how many failure systems do you build into it? And are there any workarounds? Is it so adaptable that you can engineer your way around the problem? And that's what you guys should always think about. Build in redundancy, or build in a system that is so well engineered that you've got an alternative when things go wrong. Because things go wrong all the time, and that's what, as an engineer, that's what you've got to solve, is to keep it working. So that's the most interesting thing about robotics.
Cool. Any more questions, or maybe it's time to let Bernie go get some sleep? Because in case you realise, it's currently midnight. 11:30 was over in Europe at the moment. So, yeah, so if you can all just join me in thanking Bernie again for his time this evening.
You're very, very welcome, and I just want to end on this note is that I read a book, Barry Crump, A Good Keen Man. I think the reasons that Kiwis are so well liked and so sought after around the world is because they can virtually take a problem and pull it apart, analyze it, solve it, and put it back together again. And they're adaptable and they work very, very hard. And I look around that room and I see guys and girls that are going to be the future, and working really hard at a project gets you a long, long way in Europe, and that's why Kiwis are so well liked. So, you know, take a problem, take it apart, and analyze it, put it back together again, and solve it. You guys are the future, and I wish you all the best with your studies and your ambitions. Go for it. Never give up. So thanks very much for listening. If you've got any questions, by all means, get on to Mark and I'll answer them for you, or I'll try and help you in any possible way I can.
Awesome. Thank you.
Thank you, guys.
So just a note for those people watching, thank you for everyone in the room here, just a couple of notices. So coming up in about 3 weeks, 4 weeks time, we have the International Space Apps Challenge. So this is a 48-hour hackathon that runs over a weekend. It's termed space apps, but there's a variety of challenges. So you can do robotics activities, human performance, health, obviously plenty of coding opportunities as well if there's your skill set there. There's an information weekend where if you do want to learn a little bit more, also want to join another team, you're welcome to form your own team. They can be fairly small or they can be massive, if you'll call. But there's an information session on the 29th of March at AUT in the afternoon, Sunday. And you're obviously more than welcome to ask me on one of the part of the organising committee there. Really awesome weekend, a lot of fun. You don't need to know anything about space. Half the fun actually of the weekend is actually kind of looking at a problem, researching, figuring out really what makes that work. And then what's quite interesting and really important to the international partners like NASA and ESA is actually having those different views, look at those different eyes looking at a problem and solving them from a different way. So yeah, lots of fun. Shout out, we'll have a coffee after this. You're welcome to ask me questions there as well. And our next meetup, tentatively scheduled for the 10th of May, is New Zealand's, as far as I'm aware, only space lawyer. She'll be telling us a little bit more about that. It's pretty exciting times when you look at Rocket Lab getting ready to launch hopefully later this year. All of a sudden, New Zealand needs to start thinking about, are we compliant with international law? And we are. We're a member of many international treaties, but there's a lot more treaties that are involved if you actually start launching things into space and potentially having them come down and crash land on some other country, etc. So I'm a personal fan of, I'm personally very intrigued by space law. And I think most of the scenarios get really kind of tricky and they're very interesting kind of mental exercises. So I think you'll quite enjoy that one, which will be coming up in May, or we'll send an announcement out if the date changes. So thank you very much, and yeah, you're welcome to hang around, join us for tea, coffee, biscuits, etc. Thank you very much for your time.
Thank you.
Thank you.